Okay, so we're gonna start with problem number 78, where we have a sphere with little radius of little r rotating around, well, rolling around a hemisphere with radius r, big R. And we're trying to find its rotational speed at the bottom of the hemisphere, or its omega. So the way we're gonna approach this problem is with conservation of energy. If we put 0 right here, it's gonna have 0 gravitational energy. And around here, it starts from rest, so there's no kinetic energy, it only has gravitational potential energy. And to find that, we're gonna look at the sphere a little bit closer. Pretend that's a sphere. So then we have the little sphere, then we have here, and we're looking for this h, right? So there's a theta, and then the length of this is r minus r. So h is equal to big R minus little r times 1 minus cosine of theta. So we know the gravitational potential energy in the initial point is equal to mg times r minus r times 1 minus cosine theta. Moving on. So we know at the bottom of the point, it's at 0, so it has no gravitational potential energy, so it only has kinetic energy. But there's two types. There's regular kinetic energy, but then there's kinetic energy rotational, well, or rotational gravitational kinetic energy. Not gravitational, sorry, rotational kinetic energy. So we know that the gravitational potential energy of here is equal to the sum of the kinetic energy plus the kinetic rotational energy. So it's equal to 1/2 mv squared plus 1/2 I omega squared. So we have 1/2 mv squared plus, since this is a solid sphere, we know the moment of inertia is equal to 2/5 mr squared. So we have 1/2 times 2/5 mr squared times omega squared. And we're trying to find omega in terms of r, and theta, but then we have a v here. And then we're gonna use the conversion formula that v is equal to r omega and substitute it back into this equation right here. So then we have, we're gonna write this down first. We have mg times r minus r times 1 minus cosine theta is equal to 1/2 mr squared omega squared plus 1/5 mr squared omega squared. And then we're gonna isolate omega and we're gonna add these two fractions. Let me just do that real quickly on the side. It's equal to 5/10 plus 2/5. 2/10 is equal to 7/10. So then we're gonna isolate omega squared, and we know it's gonna be equal to mg times r minus r times 1 minus cosine theta divided by, we're gonna put the 10/7 in here already because the reciprocal, when we're dividing, just multiply by the reciprocal, 7/10. And then in the denominator, we're just gonna have r squared, and the two m's cancel. So then we have omega is equal to the square root of 10/7. Oh, I forgot the g. We're just gonna pretend I didn't forget it. 10 times g times r minus r times 1 minus cosine theta all over r squared. And if we're feeling real fancy, we can rewrite it to just 10/7 g times r minus r times 1 minus cosine theta. Oh wait, this m should not be squared. That is my bad. We're gonna ignore that. And then this is all just divided by regular little r. And there you have it. That is what omega is equal to, or the angular speed.